All right, we're going to talk about probability distributions. So basic concepts of a probability distribution. So a random variable is a variable typically represented by x that has a single numerical value determined by chance for each outcome of a procedure. So a probability distribution is a description that gives the probability for each value of the random variable. It is often expressed in the format of a table, formula, or a graph. So a discrete random variable has a collection of values that is finite or countable, right? So discrete just means that it's going to terminate in. If there are infinitely many values, the number of values is countable if it is possible to count them individually, such as the number of losses of a coin before getting heads. Well, I should say heads, tails before heads. Continuous random variable has an infinite many values, and the collection of values is not countable. That is, it is impossible to count the individual items because at least some of them are on a continuous scale, such as body temperature, right? So you can have 98.7, 98.5, 98.43. Okay, so it's hard to count. Discrete means that even if you have an infinite, it's like heads and tails, you have that. So probability distribution requirements. There is a numerical, not a categorical, random variable x, and its number values are associated with corresponding probabilities. The sum of the probabilities equals 1. So if I have all the probabilities, they have to equal 1. Where x assumes all possible values. The sum of probabilities must be 1, but sums such as 0.9999 or 1.001 are acceptable because there may be some rounding issues, okay? So we want that to be up to 1. The probability of a given event is going to be between 0 and 1, so 0 is less than or equal to the probability of x, which is less than or equal to 1, for every individual value of the random variable x. That is, each probability has to be between 0 and 1. So here's our example 1, coin toss. Let's consider tossing 2 coins with the following random variable. Okay, so x is the number of heads when 2 coins are tossed. Okay, so the above x is a random variable because it has numerical value, right? Depend on chance, with 2 coin toss, the number of heads can be 0, 1, or 2. Right? The following table is a probability distribution because it gives the probability for each value of the random variable x and satisfies the 3 requirements. Okay? So I have 0 heads. So what we're looking at here is if I have my 2 coins, I could have tail, 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 head, head, tail, and head, head. So this is the distribution it is. So I would have, so there's 4 possibilities for all this. I'd have no heads, 0 or 0.25, 1 head, 0.5, or 2 heads at 0.25. Okay, so this is a probability distribution. So this is our histogram of this. So here we have 0 heads, 0.25. Probability of 1 head is 0.5, and then 2 heads is 0.2. So example 2, job interview mistakes. Okay, hiring managers were asked to identify the biggest mistakes that job applicants make during an interview. The following table is based on their responses. Inappropriate attire, 0.50, being late, 0.44, lack of eye contact, 0.33, checking phone or texting, 0.3. So does this represent a probability distribution? Okay, the answer is no, because these add up to be more than 1. It's not a probability distribution. So the idea is that probably what happened is somebody was inappropriately dressed and they were late, and maybe they checked their phone. Okay, so our probability is great. This is not a probability distribution because it is more than 1. So parameters. So the mean mu of a probability distribution is mu equals the sum of x times the probability of x. The variance, or sigma squared, for probability distribution is sigma squared equals the sum of the quantity x minus the mean, or mu squared, times the probability of x. Okay? So this is just another way to show the variance. The sum of x squared times the probability of x minus mu squared, or the mean squared. Standard deviation is going to be the square root of this. The square root of the sum of x squared times the probability of x minus mu squared. Okay? Round off rule. Okay? So these formulas are in your book. You can use them where you need them. Round off rule, round results by carrying one more decimal place than the number of decimal places used for the random x. So if I have one decimal, I'm going to round it to 2 decimals. Okay? So on and so forth. The expected value. The expected value of a discrete random variable x is denoted by E. And it is the mean value of the outcomes. So E equals mu, and E can also be found by evaluating this sum of x times probability of x. Caution. Okay, so this, be careful. The expected value need not be a whole number, even if the different possible values of x might be whole numbers. The expected number of girls in 5 births is 2.5, right? 0, 1, 2, 3, 4, 5. We add up the top 2, divide it. Even though 5 particular births can never result in 2.5 girls. If we were to survey many couples with 5 children, we would expect that the mean of girls will be 2.5. Okay, so that's a caution. It doesn't necessarily have to be the exact value. Finding the mean, the variance, and standard deviation. So here we're back to our probability of heads, right? So we're looking at how many heads we have. So we're going to find the pieces here. So find the mean, the variance, and standard deviation for the number of heads. So here we are. So we're going to go x, so the x value times our p of x. So we're going to go 0 times 0.25, which is 0. 1 times 0.5 is 0.5. 2 times 0.25 is 5. So we add those up, we get 1. So the mean is going to equal to the sum of these. So 0 plus 0.5 plus 0.5 is 1. So the mean is 1. The variance. So here's our variance. It's now going to be, we're going to find this formula here. Okay? So we're going to go 1 minus, or 0 minus my mean, square it, times my probability. So this is going to give me negative 1 squared, which is 1 times 0.25. 0.25, 0 times 0.5 is 0. 1 times 0.25 is 0.25. We're going to add those up, and that is going to be my variance. So 0.5 is my variance, okay? And then my standard deviation is the square root of 0.5, which is approximately 0.7. Use a calculator for that. Making sense of results, significant values. So significantly low values are when our value is less than 2 standard deviations below our mean. We're significantly high if we're 2 plus 2 sigma or higher. Values that aren't significant are when they fall in between there. So if we're more than 2 standard deviations above, we're significantly high. If we're more than 2 standard deviations below, we're significantly low. If we're between those, not significant. Okay, identifying the range rule of thumb. So in example 3, we found that when tossing 2 coins, the mean number of heads is 1. And the standard deviation is 0.7. Use the results in the range rule of thumb to determine whether 2 heads is significantly high rule of thumb. So using the range rule of thumb, the outcome of 2 heads is significantly high if it is greater than or equal to the mean plus 2 sigma. So here we have 1, we have sigma is 0.7, so 1 plus 2 times 0.7 is 2.24. So significantly high number of heads are 2.4 and above. So 2 is not considered significantly high. It would have to be 3, 4, 5. Well, we can't have 3. So 2 is not significantly high. And 0 is not significantly low. Okay? So with probabilities, identifying significant results with probability. significantly high number of successes. X successes of n trials is a significantly high number of successes if the probability of X or more successes is 0.05 or less. That is significantly high numbers of successes if the probability of X or more is less than or equal to 0.05. Significantly low numbers, it's very similar to significantly high. We're still going to be X or fewer is less than or equal to 0.05. So we're under that 5%. And that is probability distributions.